Hi. Um, okay. How are you? Right. Mm, I think I was talking about splitting the data set into two parts as training and testing. We were going to train a model. The first model was discussed. Um, yeah, okay. Mm, I think it's better to talk about this distribution furthermore before talking about this logistic regression model, right? Because I found that it's working fine on all these distributions. Among all these distributions, I will show you only one. Um, I have uh, interpreted the density plot of fixed acidity. It's my first variable using ggplot2 library, right? So what I'm going to do is I said that this is a, this is a right skewed uh, probability density function, and this is positively skewed distribution. So in these type of cases, we can talk about gamma distributions. So last time, yes, I said that, but I didn't introduce the distribution. No, I didn't try to find out lambda and alpha. So today, I'm going to find out both of those two parameters, and I try to set the distribution. And I'm going to compare those two, and I'll show you how far they are fitted, right? So simply I can say that I'm going to show you the probability, the best fitted probability distribution of fixed acidity, right? Hence, we can find out desired probabilities, you know, with your knowledge of statistics and probability, right? Okay. Uh, First of all, I'd like to show you the theoretical background of this, right? Mm, yeah, let me present it here. As I said earlier, there are two major types, two edges of this gamma distribution. One of that is chi distribution, and the other part is exponential, right? This should be an intermediate one, right? There are two parameters as lambda and alpha, right? Okay, so uh, will be look like this positively skewed one, right? Uh, Sorry. Okay, let me pick the pen. Right. This probability density function, uh, not only x but also alpha and lambda are parameters, right? Those are parameters. How we can write it down? Lambda to the power alpha times e to the power minus x times lambda times x to the power alpha minus 1 over gamma of alpha. So gamma of alpha is nothing else the factorial of alpha minus 1, right? Okay, so this is a distribution. So we want to find out alpha and lambda as well, right? Um, so fairly we can fit density plot with this gamma distribution, right? Because this is a continuous random variable which is larger than zero, and one more thing, uh, it is positively skewed, right? Widely skewed distribution. So I think it's fair enough to fit this distribution as a gamma distribution, right? Okay. Today I'm not going to show you the derivation of this expected value, right? One day I will show you. Expectation of the random variable is given by alpha over lambda. You know how to find it out. It's nothing else. There is a continuous random variable, therefore continuous random variable, therefore random variable times the uh, PDF, which is a function of x, alpha, and lambda, must be integrated with respect to x from minus infinity to plus infinity, right? So this function is executed when x is larger than 0, therefore otherwise it is 0, then this becomes alpha over lambda, right? And the variance of the random variable is given by alpha over lambda squared, right? Okay. Now let me pick another color. Oh, blue, right? Okay. It's being recorded, right? Okay. It's me. So in order to find out alpha and lambda, what we can do is we can divide expected value of the random variable by expectation of the random variable can be divided by uh, variance of the random variable. Then we can find out this parameter lambda, right? Hence, you can substitute that parameter on the first equation or second equation to find out alpha, right? Okay. And I'll tell you alpha is given by the multiplication between lambda and the expected value of the random variable. What we have, right? Okay. So this is what I wanted to show you, right? Hence, we can find out the gamma distribution which is related to this random variable, right? Okay. Now, let me code on this, right? Let me code on this. First of all, we have to, yeah. First of all, I have to remove this, right? Then, right. Then, I wanna find out all these essential parameters. There are two parameters need to be found out. Lambda. Let me call it lambda because it is just lambda. Expected value. Now it means mean, arithmetic mean of random variable. What is the random variable? Y fixed acidity, right? Over there is an inbuilt function in R to find out the variance of the random variable by dollars fixed acidity. Then we can find out lambda, right? Once we have found out lambda, we can derive the value of alpha. Alpha is given by the multiplication between lambda and expected value of our desired random variable, right? So let me print. Here we can print lambda. Lambda is lambda, right? Paste. There are two two ways, right? I use hence you can study this. We have two major methods to interpret it, right? Uh, alpha alpha is alpha. What I computed, right? Okay, let's see. Let's see what about lambda and alpha. Alpha is 30.97, like that. Lambda is 4.29, like that, right? So I'm going to depend on these two parameters now. Uh, I'll I'll try to distinguish these two distributions. If this is a best fitted distribution probability density function, it must be uh, overlapped with the density plot, right? Uh, Actually, we can tend up to the real scenario, but we can never achieve it. There is a convergence, right? Depending on this distribution, I'm going to call on it, right? Uh, I'll prepare this data set using a typical function which is executed under the library dplyr, right? So very significant library X. At this moment, I'm going to use a sequence from 0 to 16 here. 16, so I'll develop it from 0 to 20, right? Our space is it is incremented by 0.1, right? 0.1. Then don't forget to put the comma. It must be separated, right? I have gone through another line. It's not essential. Then your function must be assigned y equals. Do you remember the function, right? Y equals lambda to the power alpha. Insert it carefully, right? To the power alpha. Then times, right? Times exponential e to the power, right? E to the power minus lambda times the random variable times x to the power, right? X to the power. Don't forget to include that alpha minus 1 inside of parentheses, otherwise it may not work, right? Alpha minus 1. The entire expression must be divided by gamma of alpha. So gamma of alpha is nothing else, it's just the factorial of alpha minus 1, right? It's not a factorial alpha because gamma of x is given by factor x minus 1. If someone has used factorial x, it's a pi function, right? Not a gamma function, right? Therefore, there is a default function as factorial we can use in R, right? Factorial alpha minus 1, right? Okay. So I will plot it here with the help of ggplot2 data. My newly prepared dataset is K. I will add geom line. Geom line is a better interpretation way of the geometry. Geom line mapping equals aesthetic inside parentheses x equals x in my dataset and y equals y in my dataset. I would like to add a vertical line geom v line, right? V line inside parentheses x intersect equals y dollars fixed acidity, right? So yeah, I'm going to compare I'm going to compare my earlier density plot and my prepared PDF, right? Uh, so I think it's time to check it. What happened? Yeah. This should not be a colon because this is the lower boundary and this is the upper boundary is incremented by 0.1. In my earlier case, it worked because I have not used the what happened? 0.1 sequence g plot k from 0 to 20 lambda to the power alpha times exponential minus lambda x times x to the power alpha minus 1 or factorial alpha minus 1. Right, everything is fine. ggplot data is k. Let me change this. There are so many vertical lines. There must be something wrong with my vertical line. What's wrong with vertical line? What's wrong with vertical line? Geom line, nothing aesthetic. X. Let me remove this. Okay, let's run it. Okay, yeah. There must be something wrong with my vertical line I have added last time. V line. Let's see what's wrong with it. X intercept y $sign fixed acidity. Fixed acidity. Okay. What's okay. Actually, I want to add the mean. I made a big mistake, right? So I have added each of the variables as intercept x-intercept on this plot, right? It must be mean, right? I need on the mean, and I will add color as red, right? Okay. Its color is red. Now you can see it's like this, right? This is my uh, uh, probability density function based on the gamma distribution for the fixed acidity. It's my first variable in my dataset, right? Of y, right? Okay. Somehow gg title, highlighted title, PDF probability density function of fixed acidity of y, right? Okay, now I will compare it with so I will copy this one and I will show it. I will show both in same line, then you can get a better idea, right? I'm gonna paste it on this line, right? Okay, this is my real scenario, and this is my real scenario, and this is my prepared one, right? Now you can compare these two, right? If this is a best fitted probability density function, what I have prepared, it must be fitted with the real scenario, right? Can never overlap with the real scenario, but it's gonna be approximate. It's gonna be equal with my real scenario. You can see it carefully. 5 and 10, yeah, it's pretty close. It's pretty close, right? What about the peak? Peak 0.4. Yeah. There is a deviation a little bit, right? but it's fine rather than an exponential, because we were depending on alpha and lambda. Both parameters were found out, right? So like this, we can find out some distributions, right? First of all, we have to study the histogram and the density plot. Then we have to get the idea about the distribution, whatever the distribution is this, what is the shape, what is the criteria, which is pretty close to our scenario, right? So in this case, I picked the gamma distribution because of those requirements. This distribution has fulfilled those requirements, therefore I try to model it likewise, right? Okay, so like this you can find out all the others, right? Next time I hope to show you how to compute the area under these curves. Hence you can find out the probability. Let's say that you want to find out the probability of finding out uh, the wine will the fixed acidity is larger than 10, right? So we want to integrate this probability density function from 10 to infinity, right? So that's what we want to do. So next time I hope to talk about that part also, right? So in exploratory analysis, we will not talk about these type of much more deeper cases, right? Somehow, before going for the next model, I would like to uh, talk about some more EDA parts, right? Let me show you one more thing. Not only these type of density plots, histograms, and other plots, we can plot some more various type of plots like this. I think you have heard about box plots. It helps us to get an idea about quartiles, how they are spread. Let me show you how to do it. Uh, I'll use the same. I'll copy. I have copied it on my uh, keyboard and pasted, right. Uh, it's nothing else. Highlight, cut this first. This is not needed for that, right? Mm, Nothing else. We want to change. We want to change this part, right? What happened? Yeah, I have cut the code, ending part of the code, right? Okay. Now I want to change this part only. Geom underscore, if I need a box plot, geom underscore box plot, right? That's all. This is a continuous variable, so we can execute it meaningfully, right? This is box plot. What does it say? A box plot is a very strong indicator which tries to interpret quartiles, median, um, and those central tendency measurements, right? So here, the midpoint is the second quartile, and the two edges represents first and third quartiles, right? So others are considered as outliers, right? So numerically, there are so many outliers, but sometimes we cannot clean them, right? Because they are needed. They are sometimes they are recorded uh, as mistakes as a result of mistake. But here, I don't think, because there are so many recordings, so many data like that, right? So we have to think about the scenario too much furthermore. Then only we can understand whether they are outliers or not. If they are numerical, if they are outliers, we have to clean them, right? So data cleaning part will be discussed distinctly. There are so many things to be discussed, right? So now I'll show you how to do this, right? And let's say I want to show all the box plots in a single graph, in a single um, box, right? Using scale, right? There is a default function as box plot. I want to do it for all variables. Definitely, I will meet an error because there are some binary operators, non-numeric arguments, right? So what we want to do is we have to filter out only numerical values. Let's apply a function inside this function. Y is the data set, is dot numeric. We want to get on the numeric variables, right? Okay, now you can see nicely all these numeric variables are there, all these box plots are there. But the thing is, these labels are not vertical, therefore we cannot see all these variables. Each of these box plots cannot be seen clearly, right? And the other thing is they are not in the same scale, therefore we cannot identify what are having outliers, extreme outliers, and what is the most contributed variable for outliers, right? Numerical outliers. So in order to do it clearly, I'm gonna scale this. It's nothing else. I'm gonna include this numerical variable file inside this scale function. That's a default function in R, and for the command less equals to, then we can turn all these labels into vertical, right? Right now it's prepared, right? You can see, right? It seems like there is an outlier in chlorides, right? This data is too far away, right? Numerically, so we can clean it, right? So when we clean this data, single, that entire row may be cleaned, that entire row may be eliminated from the data set, right? So we have to consider so many things in this case, right? So it will be discussed distinctly, right? So now I will talk about only very important and basic exploratory parts using default functions and ggplot, right? One more thing, ggplot. Ggplot data equals line mapping. Sorry, geom. I need a scatter. Let's say I need a scatter geom point, right? Geom point mapping equals aesthetic. X equals x will be remember that we could find out some variables. Those are correlated uh, with a higher amount. What is it? It was deleted, right? Okay, I'll find it out again, right? Let me do it. Library, do you remember it? But yeah, I have the code, what I have run last week, right? Let me run it again. Library, let me check it. What was it? Do you remember it? Density and alcohol. Between density and alcohol. Okay. Let's try to plot alcohol against density, right? Let's see how the alcohol will be changed up to density. alcohol will be changed. Alcohol, right? How alcohol will be changed up to density geom points. We make it geom-like, right? Geom-line, right? Okay. Seems like this, right? Seems like this. So there may be some outliers. Once we clean outliers, there may not be outliers. Then there may be a significant strategy can be uncovered. Geo point, geo point. Let's work with geo points. This is how these points are scattered, right? This is how these points are scattered. Actually, I prefer classification, clustering, and binary logistic regression models in this case, right? So that's why I was going to talk about binary logistic regression last time, right? So then um, I got that if I could explain some more distributions before going to the model. That's why I completed that part, right? With another example, right? So I want to color it. I want to color it by color. Color equals what is the color? Color it with color. Color is the attribute in my data set. I added it last time, right? Finally, I added that column based on the kinds. There are two types of wine, right? Basically, in our data set, red and white, right? So you can see uh, there are two clusters, right? There are two clusters. So actually, when we are talking about k-means clustering and k-nearest neighbor classification, we will interpret it nicely for each of your variables like this, right? For now, just I have shown you it can be done like this, right? This is a character, and there are two types, right? It is indicated as a binary variable, right? So that's how this is filled with colors. The legend is shown on right hand side, right? So it's like this, where you can add some titles, X labels, and Y labels can be added. Right. Okay. So last time I was talking about splitting this data set. I discussed uh, what's the importance of splitting this data set into two parts. It is required in data science. Then only we can evaluate the model with the help of the testing set, right? So right, okay. I think it's time to talk about penalized logistic regression, right? Let me access my folder. Mm, right. Yeah, give me a few moments. Right. Right. Okay. Penalized logistic regression modeling, right? You can get a brief idea about this model, right? It's a very important model. Before this model, we had to talk about linear regression model, right? But I picked this data set. No need to worry. I'll give you some more examples around us, right? Using real world data, we will do, we will train all these models, right? Here, uh, let me show this clearly. Better view, right? Okay, this is a better view, right? As I explained earlier, a binary logistic regression modeling um, is for binary outcomes. It's like yes, no. It's not nodding, right? Yes or no, right? This is for categorical, or it can be for continuous, but this is between categorical and continuous variables, right? Our predictors can be continuous, right? And the response will be a categorical one with yes or no, red or white, right? Win or loss, like that, right? Uh, give permission or not giving permission. This can be used for so many streams, not only for these type of chemical, um, this type of chemistry, but also for medical streams, engineering, many fields. It's revolving around many other fields. So we can never stop talking about this biologistic regression, right? Okay, I'll talk about the mathematical intuition of this model as well. Logistic regression allows user to quantify the relationship between the outcome variable and each of the predictors through the use of probabilities and odds, right? Okay, it's true. That can be proved with my mathematical intuition. There is a relationship between our predictors and our response, right? Response will be y ordinate predictors, maybe abscissas, right? So um, response is depending on these predictors. Once we know these predictors, we can predict the response, right? The outcome can be predicted with the help of these variables, right? So the relationship between these can be derived using this model, right? Um, the next slide will show you the how we can distinguish this linear regression and logistic regression. I hope to talk about linear regression in my next with my next data set. So here we will not need linear regression, but it's a very ordinary case and essential. It's around us. It's with linear variables, and there are no some categorical responses like yes and no, right? There are no binary cases, but there are some numerical variables, right? So response also is a numerical variable, and all the predictors are numerical variables. So the relationship between those will be built up with the help of linear regression. But here we need a logistic regression. So it's like this, right? If you're trying to model the logistic regression as a linear regression, it's not working, right? Let me use, I think I can use it. I'm not allowed. So enable editing mode. Hide it. Right. Pens. Okay, what's color? Right. Okay. So you can see these observations are not lying along this desired line that can be found out. This line can be found out, but it is meaningless, right? But it is meaningless. It's not like. But in our second case, you can see there is a threshold value larger than that is put into one and less than that threshold value, zero point 0 value. It is treated as zero, right? 0 and 1 stands for yes and no, so black and white. So in our case, red and white, right? It's like that, right? I think today I can explain this theoretical background. Uh, right, you can see uh, a couple of cases we are using this binary classification model, logistic regression model will be applied in these cases, especially in banking field. They are using this biologistic regression models for predicting whether the client is eligible for a loan or not, right? Uh, in credit card fraud, they can be detected, right? And the in health yeah, in diagnosis, right? Especially in some there are some diseases, it's like cancers. There are, as I remember, there are two types of cancer cells, malignant and I don't remember the other one, right? Unfortunately, somehow there are two types. So then we can find out whether there is a higher chance of higher chance to have a cancer or not, right? Then we can use uh, some some more models rather than this biologistic, right? Biologistic regression. Right, okay. One of that model is neural network. It is used widely in those cases, right? I'll talk about that also later, right? Okay, so there are so many applications likewise, right? Right. The major thing we have to know, a little p indicates p of y equals success, right? In our case, our random variable, let my random variable equals, let my, let it be, let it be, let it be x, right? Let it be x, p of x equals 1. Let me say when x equals 1, it's a red wine. When x equals 0, it's a white wine, right? Surely, when we have more than two categorical responses, what we can do? There is another model named multivariable, multi-outcome, multivariable binomial logistic regression, right? So rather than two, we can consider at that moment, right? Okay. Uh, it's a little bit complicated, but first of all, you have to understand this. So this is given by little p. Then the other probability can be found out by getting the subtraction between 1 and p, right? It's based on the axiom of Kolmogorov, right? Okay, so it is modeled like this. Exp means e to the power, right? Exp means e to the power. Let me use my pen. Right, I think I can use it. E to the power, right? E to the power beta node. This seems like a linear regression path. Beta node plus beta 1 times x1 like that. right? This is x1 up to xk. They are our predictors. They are variables, right? We use to predict our response, our color, right? In our data set, color will be the response, but we have to predict, right? It must be predicted, right? Okay. Now it's like this. Um, then the ratio between these two, p and 1 over p, this is known as odd, right? Is known as odd. It's nothing else the ratio between the success and the unsuccess. So in our case, according to our case, the probability, the ratio between the probability of red and white, right? Okay, here I wanna clean it, clear drawing, clear drawing, right? Okay, can I go for? Can I go for? Right. It's like this, as I explained earlier, right? Um, so when you make a little p the subject, it becomes the ratio between odds and 1 plus odds, right? It's like this. It's too easy, right? So you know that odd odds is given by p over 1 minus p. When we substitute p on this equation, we can see it like this. You can get the common denominator. Once we get the common denominator, it can be simplified up to this scenario. So exponential is nothing else, it's e to the power, right? E to the power beta naught plus this part, right? Then you can get the logarithm ln of both sides, logarithm with respect to log e to the power can be taken of both sides. Then this bulk expressions expression comes down, and you can say ln odds, ln odds. We can go down, right? We can go down here. There must be, it must be here. No, where is this? Yeah, here. Here. Let me zoom it down. Yeah, right. Okay. So it comes down. Nothing else. We have made it the subject, right? And then odds, it is known as logitopy, right? So this is what we can find out with the help of logistic regression. There is a desired function in R programming which is adapted to find out this relationship, right? Okay, there are some mosquitoes, no need to worry. And I think you are bored with this theoretical background. Somehow this is what we had to know in advance, right? Before doing this, before working with this model. Sometimes uh, some guys are working with models, but they don't have proper idea about this theoretical background. I don't think it's a good influence for uh, for analyzing this data, right? Whatever the data set, it's not a good influence. Right? Okay. Now we have split the data set into two parts. Now I'm gonna train my binomial logistic regression model, right? I'll call it ML1, right? ML1 GL is the default function which is adapted for a binomial logistic regression, right? Okay. What's my response? Uh, there are a couple of ways to do this. I used to depend on this method because it's too easy on my side, right? Even it will work on you. Some guys I have seen that they used to call the formula equals this one, right? but I don't use the type formula, right? Okay, uh, once my response is color is with all the other variables, it is denoted with this dot, right? Don't forget to put this comma, right? Data. What about my data? Data equals data y, right? Y. Should we get all these variables? Should we get all these variables? No, actually not y, but train, right? We have to use train. We have to use train. And family must be defined. It's an essential parameter here. It must be binomial, right? Okay, yeah, must be a line. Let's see, color. So okay, right. We wanna first of all we wanna make it numerical variable, right? 1 and 0. I'll make it 1 and 0. Wine, dollars, color, if, else, wine, dollars, color equals red. If it is equal red, let it be 1, otherwise let it be 0. Let's check it. It was turned into that. Let's check what's wrong with it. If it's not working, we will try another method, right? We will try to convert them using another method. Color. I want to check color. Yeah, it's turning to 1 and 0, right? 1 and 0. Let's get a summary of wine color. Summary of wine color inside parentheses. Right. Let's see. Yeah, minimum 1 is, yeah, okay. Then let's print the table. Sure whether it has worked, right? Yeah, it has worked, right? So what's wrong with it? Uh, what about the data type? str, right? It's a numerical one. It's a numerical one. Yeah. The case is we have turned that into numerical value, but we forgot to do it in advance, right? Before we split it, we have to do it, right? Isn't it? Because it's still we are having the train and testing data sets with non-numerical. In our earlier cases, they are in characters with as red and white, right? So that's why it was. Now I have split them into two parts. Was here, right? No, here, right? Okay, here. Now it's all right. Okay. Now wine color is turned into this one. Now it's split into two parts, right? Okay. Right now we can try it. Right. Summary of ML1, right? And plot of ML1. This is our binary logistic regression model. Today I don't hope to explain all these characteristics and what does it say, what happened, train, train, what's going on. There must be something wrong. Let me check it. Why it's like this, quality. Everything is there, but there must be something wrong. What is it? Data train. Stable. Let's check it. Yeah, it was all of them were turned into 0 because I run the code multiple times. That's why, right? Okay, let me change it. We can run a chunk. We can run all this code at once, right? Then it will work, right? I run only needed essential codes, right? I'll run only essential codes. This is needed. That's how we have a red and white, and they were merged, right? They were binded together. These are not essential to be run for splitting. Right. Now we will split. Right. Okay. Now we will split it, right? Okay. Because when I try to run it one more time, it is free from red colors and all the others are indicated as 0, right? It says that if color equals red, just put 1, otherwise put 0. So one time it has been run. In our first time it was run and it has responded. My first result, right? And it's going to be run again. So that's why all of them will turn into 0, right? Okay. So we should be able to understand them. Otherwise, when you are doing it first time, you will struggle with these cases, right? No need to worry, no need to give up. Just do it again and again. And one day you can catch everything, right? We can never learn everything within our entire lifestyle, entire lifetime, but you can do something, right? You can realize it, you can feel it, right? That's the most important thing here. You can feel it. Then um, that's the most significant thing, right? Okay. Now, yeah. Now my model is prepared successfully. There is a meaning of this model. I'll explain it from A to Z, right? All these parameters, estimations, these coefficients, standard errors, Z values, and probability of these Z values, everything may be discussed, right? And this AIC value will help us to measure the consistency and the accuracy and the best model can be found out with the help of this AIC, and at rest we have to evaluate the model. In advance, we can run couple of models with by changing these variables. Even you can pick only desired variables, right? I have included all the variables to predict color, right? But there are some not essential variables too. I will show you how to filter them out, how to find out most contributed variables, most influenced variables for this response, right? So yeah, I think it's better to talk about that in my next session, right? Uh, this took much time rather than I desired, right? So at the rest we can predict uh, once you are given all these variables, we can predict whether it's a red or white, right? So that's the usage of this model while we are trying to actually we have prepared it. We want to optimize some parameters. We have to tune some parameters that can be done manually, and there are some desired, there are some specific libraries packages too, but I'm going to do it manually, right? Okay, so I'll explain it next time, right? There are some plots, there are some meanings, right? We have to pay attention on them too, right? Each of these plots are having meanings. We must be able to identify what's the meaning of these plots, right? We can read how far this model is fitted with this data, right? If it's not a better model, we have to go for another, right? Okay. I think for now it's enough. Next time I'll explain all these plots. Until that, okay, bye.